Okay, everyone. So we're going to move on to section 3.5. So these are limits at infinity, and I don't actually like that title for this section. It's really limits as x approaches infinity. But okay, approaches. So infinity, or actually negative infinity, depending on if you're going to the right or to the left. But in any event, limits at infinity, I guess, is okay. Just realize that infinity, of course, is not a number. So, you know, at infinity doesn't, that phrase doesn't even make sense, right? Where's infinity? It doesn't, you know, it's an idea, it's a concept, right? So here's our first example, right? We're going to consider the function f of x equals 4x squared minus 3x plus 5 divided by x squared plus 4. And the question I want to ask is, what happens as x increases, right? As x gets bigger and bigger and bigger. Okay, so let's start with x equals 0. If you plug in 0 into this function, well, you can check that, but let me try it here. So if I plug in 0, I just get 0 minus 0 plus 5. So 0 minus 0 plus 5 divided by 0 squared, which is 0 plus 4. So I really just get 5 over 4. Yeah, that's a 5, not an s. And 5 over 4 is the same as 1.25. So that's where this 1.25 here comes from, right? And so you can plug in other numbers like 10, 100, 1,000, and I'll save you the trouble of doing that. You can obviously just use a calculator to do this. So you plug in the numbers, and the y coordinates are these, right? So I think now we can sort of ask the question, what happens as x gets bigger, right? I mean, of course, bigger is a relative phrase. You know, what's big? 10, 100, 1,000. A million you might think that's bigger. So as x gets bigger, right, and certainly 100's bigger than 10, 1,000's bigger than 100, 10,000's bigger than 1,000, and so on. So the y coordinates are doing this, right? So at 10, y is 3.6. At 100, y is 3.96 or 3.97. And at 1,000, it's 3.997, and so on, right? So you can see that, right, as x gets bigger and bigger, the y values are not getting bigger. Well, I mean, they're getting bigger, but only slightly, right? So if you were to plug in, say, a million, you would probably get 3.999997 or something pretty close to that, right? So 3.999999, that's getting close to the number 4, right? So the way to write this is, right, we write the limit as x increases without bounds. Now that's the proper way to say it, but you can also just say x goes to infinity or x approaches infinity, right, of the function f of x, and this is in example 1, that's the function. So what happens to f of x? Well, it gets close to the number 4. So this limit would equal 4. Right? And notice that you can go the other way as well. You can go in the negative direction when x is negative 10, negative 100, negative 1,000, right? So going in the opposite direction, in the negative direction, the y values still get close to 4, right? They're slightly bigger than 4, but, right, as x continues to decrease in the negative direction, right? So negative 10,000, negative 1 million, negative 1 billion, and so on, the y values seem to be getting close to 4, right? So we can also say the limit as x goes to negative infinity of the same function is also 4, right? Now, in this example, you can think of that as maybe a coincidence, that whether you're going to positive infinity or negative infinity, you get the same value, you get 4. That may happen, that may not happen in other functions. Okay, so just keep that in mind, that this only applies, that these end up being the same value for this particular example here. Okay, so I hope that at least gives you some intuitive idea of what we mean by limit as x approaches infinity or negative infinity. Infinity just means you're going to the right forever, and negative infinity means you're going, to the left forever. Okay, so what happens to the y values, right? Okay, so the formal definition, the mathematical definition is here, and you may want to look at it. It's the epsilon. There's no delta here, but there are epsilons, and just briefly, just to explain what this means, right? So the definition as x approaches positive infinity, right, of f of x, that's going to be some number L, if for every epsilon there exists an m positive, some positive n, m, such that this absolute value, the difference between f of x and L, is less than epsilon whenever x is bigger than m. So again, I don't really want to get too deep into this. This is really analysis here. But all it's really saying is, it might be helpful to look at a graph here. And I'm not going to use this particular function, but in general, right, here's the x-axis, here's the y-axis, and then we have some function. Let's say the graph, looks like this. So this is x equals 1, x equals 2, x equals 3, x equals 4. So let's say this is x equals 2 here. And just for reference, this is all y equals 2. Suppose the graph were to look something like this. Be careful not to get too close to this line here. So what we have is a graph where as x gets bigger, the y values get closer and closer to 2, right? So here it might be, 2.1, here it might be 2.01, here it might be even closer, right? So 2.1, let's say 2.05, 2.0001, and you're just getting closer and closer to this horizontal line y equals 2, right? So what that means is the horizontal line y equals 2 is a horizontal asymptote. So in fact, we use, I'm trying to spell it out here, horizontal asymptote. All right. So what that means is as x, so let me write out the limit again here. So we have the limit as x approaches positive infinity of whatever this function is. I'll call it g of x. Right, so this is the graph of some function g of x. That's going to equal 2. It's going to equal to 2, the number 2, right? So again, that doesn't maybe explain this definition here, but here's the idea, right? Suppose we want to be very close to 2, right? We want to be within epsilon of 2. Let's say epsilon is 0.1, right, or 1/10. Okay, so we want to be within 1/10 of 2. So we can be as big as 2.1 or as small as 1.9, right? And you can see that if I pick some x over here, the y value is certainly not going to be between 1.9 and 2.1. It might be 3.5 or 4 or 3.9 or something, but certainly not between 2.1 and 1.9, right? So this statement here is basically saying that our g of x, can I squeeze that in here, right, minus our limit. Now our limit here we said was 2, so L is 2 here, has to be less than 0.1. So this x here would not qualify for that, right? So this is not true for all x, but it has to be true, and this is the important part, whenever x is bigger than some number m. So that m might be very large, right? It might, right? It might not be, this x here. This, I don't know, x might be 5 or 6. It might not even be true for x equals, 7 or 8. But if I said, I need to make that clear here, right? If this is 2.1, then that just barely qualifies. So this might be x equals, let's say x equals 10 or something. So x might have to be bigger than 10 in order for this statement to be true. So eventually, and that means as x is big enough, bigger than some number m, eventually your y values will all cluster around this limit here, 2, right? And so it has to be close enough to 2. How close? Within epsilon. Okay, so that's the definition. And there's a similar definition for going to, if you notice, the only difference here is you're going to negative infinity. And so here x has to be less than some negative number. So way over here on the left. But it's a very similar definition, right? So if you understand one, you understand the other. And so the point is not to go too deep into this, because I'm not going to ask you questions about, epsilons or deltas. But this is the formal definition of what it means to be a limit as x goes to infinity or negative infinity. For our purposes, I'm more interested if you understand this, that using the table here to calculate values of x when x is getting very big, going to infinity, or when x is very, well, I'll still say big, but big in the negative sense, going to negative infinity, right? So there are two different limits, one going to positive infinity, one going to negative infinity. And the fact that, they're both equal to 4 in the first example is a coincidence. They don't have to be equal here in some cases. Okay, so I mentioned this horizontal asymptote, and you can see that that's essentially the definition of a horizontal asymptote, right? What is a horizontal asymptote? Well, it's a horizontal line, y equals L, right, in such a way that as x either goes to positive infinity or negative infinity, the limit will be L. And that just means that the graph will get closer and closer to the horizontal line. In this case, y equals 2. In the case of example 1, it would be y equals 4. Right, so you just have a different asymptote for different functions, right? So it depends on what your f of x is, right? And of course, some functions don't have horizontal asymptotes. If you just look at the example, say y equals x, that does not have a horizontal asymptote, right? The graph, terrible looking graph, but I'll do the best I can here. It's just going to be this line here, right, going on forever. So as x gets bigger, the y values just get bigger. They don't get close to any one particular number, right? So in this case, you could say the limit as x goes to infinity of y, which is just x here, well, as x goes to infinity, x goes to infinity. So you can say the limit is infinity. But by that, we really mean the limit does not exist, right? Infinity is not a number. It's not like 4 or 2 or 7.8, right? It's not a number. So this is somewhat informal here, but we've already explained that, right, the limit can be infinity or negative infinity. That's just a very specific way of saying that the limit fails to exist. The limit does not exist. Okay? Right, and, to use the same example here, if we take the limit as x goes to negative infinity of x, well, now negative infinity is to the left in this direction. What's happening to the y values? They're not going up, they're going down in the negative direction. So here you would get negative infinity, which is just a more specific way of saying the limit does not exist. It does not approach one particular number. So I hope that helps at least explain the concept of limits approaching infinity or approaching negative infinity. Or as the book would say, limit at infinity, but I already told you that I don't prefer that language, but it's okay if you don't take it too seriously that, there's no at infinity, right? Where is infinity here on the picture? There isn't any, right? You have to just keep going to the left forever and ever, and you're never going to get there, right? So it's an abstract concept, right? Infinity is just the idea that you can keep going, right, to the right forever. And negative infinity is the same idea, but now going to the left forever. Okay? So I hope that helps. Okay, so this is still section 3.5. So now we're going to look at some examples. Before we do that, there's one important theorem, one important property that we're going to use over and over again. Okay, so this property is the following, right? It says that if you have r, a positive rational number, right? So that could be a whole number like 3, it could be a fraction like 1/2 or 2/3, and c is any real number, then the limit as x approaches infinity of c divided by x to the r is equal to 0, right? And furthermore, if x to the r is defined when x is negative, then you also have that the limit as x goes to negative infinity of c over x to the r is equal to 0. Okay, so what does that, right? What does that mean, and how does that work? So let's look at first example. Suppose we want to take the limit as x approaches infinity of 7 divided by x. Okay, so what's the limit as x goes to infinity of 7 divided by x? Well, I mean, on one sense, you can just apply the theorem, but let's see if we can understand what we're doing here, right? Remember what it means as x is going to infinity. X is getting bigger and bigger and bigger. So the question is, what's happening with 7 over x, 7 divided by x, right? And maybe I shouldn't have picked 7, but that's, all right, that'll work here. So here's the idea, right? Let's just do it the old-fashioned way. Let's make a table, right? So let's plug in values of x, and I should do a vertical one, but too late. It's going to be horizontal, right? So what's big, right? Obviously 10 is not very big, but we could plug in 10, right? And so if you plug in 10, you just get 7 over 10, or 0.7, right? So let's get bigger. You can do 100 or 1,000, but let's make it a lot bigger. Let's make it 10,000, right? So you have 7 divided by 10,000, which is 0.0007. Did I have enough zeros? So let's see. It's 10, 100, 1,000, 10,000. Yep, I think I have the right number of zeros. And you can see that this is a fairly small number. So what happens if you plug in an even bigger number, like 1 million? Right? Well, you get 7 divided by 1 million. I think I have too many zeros here, right? 6 zeros, right? But as a decimal, I'll write it under here. As a decimal, that's just 0.000007, right? And you can see that's a fairly small number. So what's happening as x is getting bigger here, you can make it, say, 1 billion, 10 to the 9th. So 7 divided by a billion is just going to be 7 times 10 to the negative 9, which is an even tinier number, right? So what's the idea? These numbers are getting bigger, x's are getting bigger, but 7 divided by x seems to be getting smaller and smaller. They're getting close to 0, right? So I think a reasonable answer to this question is that this limit is 0. Okay? So, I mean, that doesn't prove this theorem here, but at least it shows that it's not wrong, right? We have our constant c is 7, and r, of course, in this case is just 1, right? X to the 1 is x. R, 1 is a rational number, right? So that gives us a pretty good idea of what's going on here, right? If the numerator is just a number, a constant, and the denominator involves some power of x, well, as x gets bigger, the denominator gets bigger, but that means the fraction gets smaller, right? As the denominator gets bigger, like in this example here, 7 divided by 1 million is a very small number, right? And 7 divided by a billion is an even smaller number, and so on. 7 divided by a trillion is even smaller. So, yep, as the denominator gets bigger, the whole fraction gets smaller. It goes to 0, okay? So I think that sort of is a reasonable idea here. Again, it doesn't prove it, but we're not going to prove it. We're just going to use this fact because it's very useful, actually. We're looking at more examples. So let's look at a second example. suppose we have the limit as x goes to, let's make it negative infinity, and let's just do 1 divided by the square root of x. Okay, so what would that limit be? All right, so first of all, let's think of the square root of x. Again, we didn't take the limit yet, so I'm going to copy limit down. Everyone has been great at continuing to write limit until the very end, until you actually take the limit. So this is 1 over, so c is 1. And what's r, right? So this is x to what power? So if you remember square roots have an index of 2. This is just x to the power 1/2, right? So here our r is just 1/2. But 1/2 is a rational number, so this should still qualify, right? Okay, so we could make a table here as well. We'll do it over here. So here's x, and here's 1 over the square root of x, right? And remember, here we're going to negative infinity, so this is backwards. 0 is way over here, right? So what happens when we plug in 0? Well, we get 1 over 0, which is undefined. So that doesn't help, right? So what happens if we plug in something like negative 10, which is not very big, but it's a start. We get 1 divided by the square root of negative 10. And if you remember, the square root of a negative number is imaginary, and well, that doesn't seem to help. So it doesn't matter how big you get here. If you plug in negative 10,000, you get 1 over the square root of negative 10,000, which is still imaginary. And so we're not going to count imaginary numbers here. For our purposes, you can't graph them, for example. They're not on the y-axis. So essentially, these are not in the domain of the square root function. And so that's the important key here. If this quantity, the x to the 1/2, the square root of x, is defined when x is negative, then the limit would be 0. So if you read this too carefully and you think, well, right, that this would have to be 0 according to this theorem, be careful. Read this carefully, right? The function, the square root of x, is not defined when x is negative. We know that because we get imaginary numbers, right? And so this is not equal to 0. In fact, we just have to give up and say that this limit does not exist, right? And not because it's infinity or negative infinity. It's just it just doesn't have a value. There is no y value here. There's no real y value. So so that's what could go wrong here, right? If the things like square roots or fourth roots are not defined when x is negative, or any function that's not defined when x is negative, right? If you might remember the natural log function from pre-calculus. This function has a domain of x greater than 0. In fact, that's the same domain as this. X has to be greater than 0 here. That's right. And so it doesn't make any sense to take the limit as x goes to negative infinity because it's not defined there, right? Okay. However, continuing with this example, let's take the same limit, but now going to positive infinity of 1 over the square root of x, right? So now we're going to reverse this, and here's x, and here's 1 over the square root of x. That's a terrible looking x. Let me try that again. 1 over square root of x, right? So a very similar table here, but now we're going to be using positive numbers like 10, right? So 1 over the square root of 10, I don't know, it's something like 0.2 or 0.3, but not very small, right? If we plug in 100, you just get, the square root of 100 is 10, so you just get 1 over 10, 0.1. If you plug in 10,000, you get 0.01. Excuse me. So yes, you can plug in bigger numbers, 10,000, 100,000. Let's do 1 million. And you get 0.001. So x is getting very, very much bigger here. X is going to infinity. And these numbers are getting small, but not very quickly, right? You need a lot more zeros for x than you get for y. However, 0.001 right? Eventually you get 0.0001 and so on. So these numbers are getting close to 0. So in fact, this limit is actually equal to 0, right? So if you're going to positive infinity, right, it almost doesn't matter what the r is here, right? This will always be 0 as long as the numerator is just a number, just a constant, right? If it involves a power of x, then that's a separate question, right? But if you're going to negative infinity, you have to be careful, right? Things like the square root is undefined there, or the logarithm is undefined. Again, that doesn't apply here, but, you know, any function with a domain that doesn't involve enough, you know, x going to negative infinity, then you just give up and say the limit does not exist for those. Okay, so I think we'll look at another example here. Let's make this example 4. Right? Suppose we have the limit as x goes to, let's keep it positive here, positive infinity. So yeah, we want to make it a little more challenging here. How about x cubed minus 4x all over 2x cubed plus 3x squared. Okay, so yeah, way more complicated than, you know, 7 over x or 1 over square root of x. But it is a rational expression, right? It is a rational function. And so we should be able to figure out the limit. Again, one way is to make a table. But at some point, that's going to get very, very cumbersome to do. It is kind of tedious, right, to have to plug in, right, a lot of values here to see the pattern. You know, in some cases, the pattern might be obvious. In other cases, it might not be, right? So rather than make a table, we're going to use this property up here, this theorem 310. Now, we can't use it directly because notice the numerator is not a constant. It's not c here, right? It's a function of x, right? So we can't really use this property directly. However, we can do a little bit of algebra here and maybe rewrite it in a form where we can use this property. Again, I erased the property, but it's up here, right? So notice what we need is the numerator to be a constant, and we need all the x's in the denominators. So obviously we have x in the denominator here, but we also have x in the numerator, and so that's not going to work. But so the way we're going to do this is we're going to look at the biggest power in the denominator. In this case, the biggest power in the denominator is 3. Obviously, that's also the same is true for the numerator, but that's a coincidence, right? In this problem, yes, the degrees of the numerator and denominator happen to be equal, but they don't have to be, right? It's certainly not for the first 3 examples here. The degree of the numerator for example 1 was 0. The degree of the denominator here is 1. Okay, so they don't have to be the same, but they just happen to be the same in this example here. So you take the 3, the biggest power in the denominator, and what we're going to do is multiply numerator and denominator by the same thing. So put parentheses around everything here. And in the numerator, I'm going to multiply not by x cubed, but 1 over x cubed, right? And the same in the denominator. So I'm just multiplying by 1, so I'm not going to, right, I can cancel these if I want. But the idea is to rewrite this expression in such a way that I'm getting all the exponents in the denominators. After all, right, that's what we're looking for here. We're looking for the x's to be downstairs in the denominators. And this should allow us to do that, right? So now what's our fraction going to look like here? So if I distribute this, x cubed, well, okay, let me write it out. X cubed divided by x cubed minus 4x divided by x cubed, right? And then do the same thing in the denominator. When you distribute this, you get 2x cubed divided by x cubed plus 3x squared divided by x cubed. Okay. So that's just expanding all this out, right? Distributing what's on the outside here. Okay, so our next step is to simplify all this, right? Obviously, x cubed divided by x cubed, that's just 1. So as our next step, again, we didn't take the limit yet. We'll do that later. This x cubed divided by x cubed, that's just 1, right? and 4x divided by x cubed. So one of the x's cancels. We still have a 4 in the numerator, but in the denominator, right, we have 2 more x's. So 1 minus 3 is x to the negative 2, or in the denominator, x to the positive 2. Right? And you do the same thing for the denominator here. 2x cubed divided by x cubed. Obviously, the x cubes just cancel, so this is just 2. Plus 3x squared divided by x cubed is going to be 3 divided by x. Okay, so is everyone okay with that? That I'm just simplifying all this? All right, so now we can come back. Hang on to this thought for a second. We're going to come back to this property here. And if you notice, as long as the numerator is just a constant, the denominator is some power of x. And that's going to be true here, right? So here we have a constant c, which is just 4 in the numerator, divided by x to a power r. Here, r is 2, right? Well, according to this theorem up here, that this limit has to approach 0. Right? So this approaches 0. And the same is going to be true here, right? 3 over x. C is 3. This is x to the r, where r is 1 in this case. But according to that same property, this also has to approach 0. Right? So what does that mean for the result here? Well, this is still going to be the limit as x approaches infinity of 1 minus 0 over 2 plus 0. But that's just 1/2, right? So the limit of 1/2 is 1/2. Now we can actually take the limit. So we get our answer. We get 1/2. So that's the, so I messed up the original problem here, but I can copy it down again. The original example was the limit as x approaches infinity of x cubed minus 4x all over 2x cubed plus 3x squared. Now we know through this calculation here that this limit is 1/2. Okay, so I hope that helps. Now, some of you, very clever, if you remember from pre-calculus, are like, well, I knew that already. I knew this was 1/2 because in pre-calculus, you taught us that if you have the same power in the numerator and denominator, you just divide the leading coefficients. The leading coefficients here are 1 over 2. So according to our pre-calculus method here, if we want to find the horizontal asymptote, all we have to do is compare the degree of the numerator and the degree of the denominator. When they're the same, we just divide the leading coefficients. 1 over 2 is 1/2. Right? And that's fair enough. After all, when we're finding a limit, remember we're finding the horizontal asymptote. If we're finding the limit as x goes to infinity, I should say, we're finding the horizontal asymptote, right? So if you want the horizontal asymptote for the first example, it would just be y equals 0, right? For example 2, you also have a horizontal asymptote of y equals 0. Now remember, it doesn't have to be true that both the limit going to positive infinity and the limit going to negative infinity have to be the same value. In this case, one exists, one is 0, and one does not exist. But if you remember, for the horizontal asymptote, it's only one of these have to be true, right? One of these have to be a limit. And in fact, if you do have a limit here, let's say the limit is -6, then you have two different asymptotes, two different horizontal asymptotes. You have one y equals 0, and then you have the other y equals -6. But for example 2 and 3, right, we only have one horizontal asymptote, y equals 0. Okay, so in any event, going back to example 4, this function here, again, I keep messing it up, but this function here has a horizontal asymptote of y equals 1/2. So yes, that is the same that you would get if you just used the methods from pre-calculus, right? And I'm going to do another example showing you the same thing here. Just realize that the question wasn't what is the horizontal asymptote, the question is to find the limit. And if that's the question, I want you to calculate it algebraically, right, using this process here, right? And we'll do a couple others just so you get the hang of it, but that's the idea. This is how I want you to calculate these limits. All right, so I guess we're up to example 5. Hang on here. So example 5. So let's take the limit as x goes to, let's make it negative infinity now. Yeah, let's do x squared minus 3 divided by 2x plus, I changed my mind. Let's make it, because we did 2 already, let's make it 4x minus 1. Okay, so we want to find this limit here. Okay, well, so we're going to do the same trick that we did in this problem. We multiply the numerator and denominator by the same thing, 1 over x to some power. So what is that power here? Is it going to be 1 over x squared? So remember, last time I said that you pick the biggest power in the denominator. The biggest power in the denominator here is not 2, it's x to the 1. Okay, so we're going to divide top and bottom by x to the 1. So I'm going to rewrite all this. I know it's a pain to rewrite it, but that's part of the process here. So we have x squared minus 3, I'll put it in parentheses, divided by 4x minus 1, right? So what we're going to multiply top and bottom here by is 1 over x, not 1 over x squared. That won't quite work out right, but 1 over x to the 1, because 1 is the power in the denominator, the biggest power in the denominator, right? The degree of the denominator. Okay, so now distributing this to each term in the numerator. Right, still going to negative infinity. We're going to get x squared over x. And you can do this in your head, right? X squared divided by x is just x. Minus 3 divided by x. Right, so essentially I'm skipping this step up here. Right. Maybe I shouldn't in the second example, but all right. So I'm cutting corners here. Likewise, 4x divided by x is really just 4, because the x's cancel. Minus 1 times 1 over x is still 1 over x. Okay, so I multiplied this out and I simplified all at once. Right, so and feel free to do that. You don't have to go step by step here, as I did in example 4. Okay, so now we can go back way up here. Sorry to make you dizzy here, but we're going to apply this same property. We have a number in the numerator and x in the denominator, right? So that's what we have here, right? That's what we have here. C over x to the r. This is, C is 3, r is 1. So this has to approach 0. And likewise, 1 over x also has to approach 0 as x goes to negative infinity, right? Either infinity or negative infinity, right? Because this is going to be defined positive or negative infinity. There's no square roots here. Okay, so what does that bring us here? So that brings us to the limit as x goes to negative infinity of just x minus 0, right? X minus 0 over 4 minus 0, or just x over 4. X over 4, right? So what happens to x over 4 as x goes to negative infinity? Well, this, right, certainly does not go to 0. It doesn't go to 1/4, right? X is not 1 here. X is getting bigger and bigger, but in the negative direction. So if x is negative 1 million, right, this is going to be negative 1 million divided by 4, which is some big negative number. I think it's negative 250,000, right? And if x is a billion, then you get negative 250 million. So you're getting negative, really big numbers, right? So this is just going to negative infinity, right? In other words, this limit actually does not exist because this does not approach any one particular number, right? It doesn't approach 1/2 or 7 or 0, right? It does not exist, right? The numbers get bigger and bigger in the negative direction. Okay, so you can say negative infinity or does not exist. Again, I would prefer negative infinity because that's a little more descriptive. Does not exist could mean many things, right? It could mean it approaches a positive infinity, it could approach negative infinity, or as in example 2 here, it just doesn't approach anything, right? It's not even defined for negative x. Right. So here it's defined, it's just that you know, as x goes to negative infinity, x over 4 goes to negative infinity as well, just a lot slower than x does, right, by a factor of 1/4. So I hope that helps, right? So that's example 5. I think I'm going to do one more example for this video, and then I might make a separate video for more complicated examples. So yeah, so let me do one more example in this video. I'll call it example 6. And then the next video, I'll revert back to example 1. So yeah, let's make this, I think, a little more challenging. All right, how about, oops, sorry. We'll take the limit as x goes to, we'll go back to positive infinity. Let's do the sine of 2x divided by 3x. Yeah, you can have trig functions as well, right? So we haven't seen that yet, at least for these types of limits, but we've had problems before with trig functions involving limits. So if x were approaching 0, I hope you know how to do that. We've done many of those in chapter 1. But here we're going to negative infinity, so that's a slightly different problem here, right? Okay, so what do we do here? So we have sine of 2x over 3x. So obviously the biggest power in the denominator is 1, x to the 1. But the numerator, the sine of 2x is not a constant. It's not c. So if I can go way back up here for a second, we can't apply this theorem directly because c is a number, right? Sine of 2x is not a number. It depends on x. You know, if you remember, sine wiggles back and forth like this, right? It's a terrible graph, but it's not a constant. That's the point, right? So we're going to have to be a little bit more clever here, right? Sine of 2x may not be a constant. However, and if I drew a better graph, I can do this a little better here. So here's the x-axis, here's the y-axis. Basically, the sine graph is bounded. It's between 1 and negative 1, right? So if you remember, or you may not remember, that the range of the sine function is between positive 1, so less than positive 1, and bigger than or equal to negative 1. Okay? And that's true regardless of whether it's sine x or sine of 2x or sine of 3x. So you can stick a 2 in here, and that doesn't affect the amplitude of the sine function, right? In this case, it's still 1 and negative 1, right? It has to do with the 1 in front here. There's an invisible 1 sine 2x, right? Okay. So how does that help us here? Well, for this problem, let me leave this up for now. We're going to use the fact that, right, the sine of 2x varies, but it's between negative 1 and positive 1, right? So this expression here, well, yeah, sine of 2x divided by 3x, this is going to vary between 1 over 3x and negative 1 over 3x. Okay? So maybe now you see where this is going. If I look at this, if I take the limit of this as x goes to infinity, this goes to 0, right? You have a constant in the numerator and x to the power 1 in the denominator, right? So that goes to 0. On the other hand, on the left here, we have another c. c is negative 1. Well, technically it's negative 1/3, right? C is 1/3 here, c is negative 1/3, but it's just a number, right? And you have x in the denominator, x to the power 1 in the denominator. So it's just a different c in this case, but this also goes to 0. So, right, if the right side goes to 0, the left side goes to 0, this middle here also has to go to 0, right? Why? It goes way back to chapter 1. This is the Squeeze Theorem, which we haven't used much until now. Squeeze Theorem. So if you remember what the Squeeze Theorem says, very briefly, let me remind you, if you have 3 functions, say f, g, and h, and they vary this way, right? So g is in the middle, f is less than g, and g is less than h, right? I'm going to run out of space here, so let me move this down a little. If you have the limit as x approaches c, or although c could be infinity here, so let's use infinity, of f of x, if this is some value L, and that happens to be the same as the limit as x goes to infinity of h of x, right? Then, because g is in between, that guarantees that the limit as x goes to infinity of g of x also has to be L. So what's our L in this case? Sorry for the sloppiness, but our L in this case here is 0. Because it's the same for f of x, which is the negative 1 over 3x, and the h of x is 1 over 3x, positive 1 over 3x. And the g of x is what's in the middle, the sine 2x over 3x. Well, that also has to go to 0. So by the squeeze theorem here, right, now we know that this limit, has to equal 0, right, because of the squeeze theorem. Okay, so yeah, this was a trickier one because, well, if you forgot the squeeze theorem, then there's really not much else you can do here. Obviously, you could also fall back on making a table. We've done that many times. So these are the y values. These are the x values. So you just plug in very big numbers like 1,000, 1,000,000, and see what happens. Effectively, you're going to get very small numbers here. I don't know exactly what, but, 0.00 something, 004 maybe. And then here you're going to get 0.000000. That's going to go on for a while, right? So as x goes to infinity, the y values just get smaller and smaller. They go to 0. Okay? And you might say, well, isn't that the same thing that you would get if you applied this theorem up here? Right? These limits go to 0 as long as the numerator is a constant. The problem is, right, this numerator here, the sine of 2x, was not a constant. So it does have the same effect, but you can't apply that theorem directly because this is not equal to c. Right? What saved us, however, was the fact that the sine function is bounded between -1 and 1. Right? That's way up here. That's this statement up here. And because it's bounded between -1 and 1, our c's were -1 and +1. And so because those limits both go to 0, that forces the middle to go to 0 by the squeeze theorem. So it's really the squeeze theorem that we had to use in addition to this original property up here. Right? We use this for our f and g. For our f and h. Right? Here f of x was this mess here, and the h of x was this mess here, the 1 over 3x, and the f of x was -1 over 3x. And the g of x, the g here, is what's in the middle. That's the sine of 2x over 3x. Okay, so I hope that helps. Again, I'll make another video and we'll do a couple more examples using this property here. But for now, I hope this gives you at least the idea of how to calculate limits going to infinity or -infinity. Okay, so continuing with section 3.5, I'm just going to do an example. This is example 10 from my notes, so this is not in the book as far as I know. I might have stolen it from the book, so it might be an exercise somewhere in the book, probably an even one. But this is going to be kind of a tricky one, okay? So I'm going to go through this as carefully as possible. And I wouldn't expect a lot of these on any tests, but, if I'm going to give you a challenging one, it might be something like this. But if you can handle the ones in the previous video, you should be okay. So here's the example, right? We want the limit as x goes to -infinity of 3x minus 2 over the square root of 2 times x squared plus 5. Okay, so yeah. So first let me just copy down the problem so we can see it a little more clearly here. We want the limit, sorry about that, the limit as x approaches -infinity of 3x minus 2 all over the square root of 2x squared plus 5. Plus 5. Okay. So, yeah, so this is a little different because we didn't have square roots. Well, we did have simple examples like 1 over the square root of x, right? And yeah, since the numerator was just a constant, we can apply that theorem exactly here, but not in this case, right? Because the numerator is not a constant, right? So what we could do is say the same trick that we did in some of the previous examples. We can take the biggest power in the denominator and divide top and bottom by that, right? So let me set that up here. Give me a second. Sorry. X goes to negative infinity. I'm going to put in parentheses 3x minus 2 for the numerator. And in the denominator, you know, I could use a power of 1/2 here. I don't have to, but let's do it that way. So 2x squared plus 5, all raised to the power 1/2. Right? So what's the biggest power in the denominator? Well, if you're thinking x squared, that seems to be true, right? So you think our r is 2 here, but remember, you're also taking it to the power 1/2, right? So if I have x to the 2, and then I raise it to the power 1/2, well, that's just x to the 2 over 2, which is x to the 1. So we're not raising the denominator is not really a power of 2 here, because we're taking the square root of it, it behaves a lot more like x to the 1 rather than x to the 2. So yeah, so be careful. If you multiply top and bottom by 1 over x squared, it's not going to work out right. We just want 1 over x. So the square root of x squared. Okay, so yeah, so same trick that we did earlier, but now we can do the same thing here. We're going to distribute the 1 over x, right, like this. So we get 3x over x, which is just, well, okay, so I'll do this one more time. 3x over x minus 2 over x, right? Now, what about the denominator? So this is going to be a little tricky. I'm going to go back to the square root here. So I only wrote it as x to the 1/2 to illustrate that we're not doing x to the 2, but x to the 1 here. Okay, so now, so yeah, I'm just going to write it this way. 2x squared plus 5 all over x. Okay. And so that doesn't really seem to help at this point, right? We're going to have to simplify this further. And this is where it's going to get tricky. This is where we're going to have to deal with this negative infinity here, right? So as an aside, I'm going to try this. Right? So I'm going to go over here, and I'm going to remind you of when you take the square root of x squared, you don't really just get x, because it depends on whether x is positive or negative, right? What you actually get is the absolute value of x, right? Which is, if you remember, x, if x is positive, or 0, right? And negative x, if x is less than 0, right? So, let's reverse this, right? If x is greater than or equal to 0, then x is really the same thing as the square root of x squared. On the other hand, if x is negative, negative x is the square root of x squared, or x is really the opposite of the square root of x squared. Okay, so that's what I'm going to do here. I'm going to take this x and change it to this. So why are we picking the bottom one and not the top one, not the plus? Well, remember, x is going to negative infinity here, right? Right? So if x is going to negative infinity, you can be sure all the x's are going to be less than 0, going to be negative. So that's why we need a negative sign here. Okay? So my next step is just to change this x to negative square root of x squared. So I'll do that down here. Hey, oh, while I'm at it, 3x over x is just 3 minus 2 over x. Okay. But now we're going to get, so the numerator of the denominator is still 2x squared plus 5. That didn't change anything yet. And now we have negative square root of x squared. That's an x. Okay. And so that negative, right, it's just a negative fraction here, right? Okay, so change that to a plus. That's a minus. And we have a positive divided by a negative, so that negative can actually come clear all the way in front of the limit. So this is just negative limit x goes to negative infinity of 3 minus 2 over x, and then all divided by, so what's this going to be, right? This is going to be the square root of 2x squared plus 5 divided by x squared, right? You can combine them all into a single square root. And we can even go further here, right? This is the square root of 2x squared divided by x squared plus 5 divided by x squared. Sorry, that's an x. And 2x squared over x squared is just 2. And then plus 5 over x squared. I think I'll leave that alone for now. Right. So we rewrote the denominator as the square root of 2 plus 5 over x squared. So, okay, so that was a lot of algebra. So let's just take a deep breath here and, look at where we've been here. So we're calculating this limit, and the first step is to figure out what to multiply top and bottom by, in this case 1 over x, right? And then, again, the tricky thing here is you have to realize that because you're going to negative infinity, we're not changing x to the square root of x squared, we're changing it to negative square root of x squared. Okay, so that's where we get this negative sign in front here, right? See that? Okay. And then we just did a lot of algebra here, and we simplified all of this to this form here. Right. Okay. Well, now we're in good shape, because now notice that we have constants in the numerator and x in the denominator. So by that same property from the last video, 2 over x, as x goes to infinity or negative infinity, either way, this has to approach 0. Likewise, in the denominator, this 5 over x squared, c over x to the r. So c is 5, r is 2. But either way, that approaches 0. Right? So what's left over then? Give me a second here. What's left over is negative. Right? The negative is still in front here. Right? So don't forget that. Limit as x goes to negative infinity of 3 minus 0 over the square root of 2 plus 0. But now there's no more x's, so this is just going to be the constant, 3 over square root of 2, right? But be careful, there's that negative in front, so it's actually negative 3 over the square root of 2. And that's our final answer, right? So that answers the original question. What is the limit as x goes to negative infinity of 3x minus 2 over square root of 2x squared plus 5? That's a mouthful. Well, now we have our answer, right? The answer is way down here, negative 3 over the square root of 2. Look, I already told you many times that you can leave your answer with an irrational denominator. If you were to simplify this, you would get negative 3 square root of 2 over 2. And in fact, if the book has an answer key, the book would write it this way as well. But you know how to rationalize the denominator, I assume. Just be aware that on a test, I am not picky about that. You can write it either way at this point. So, yeah, I hope that helps. Again, this was a tricky problem. This I would say is a hard problem, especially because you have to wrap your head around this the absolute value of x and the square root of x squared, right? They're the same thing, but that means that x has to turn into this negative square root of x squared instead of a positive. And that's where the negative sign came from, right? That's why this is negative here and not positive. Because you're going to negative infinity, you get this negative sign. If we were going to positive infinity, hang on. Let's treat that as a separate example here. If we're going to say the limit as x goes to positive infinity of the exact same expression, 3x minus 2 over the square root of 2x squared plus 5, well, I think rather than go through this whole thing again, I think we can say pretty easily that the only difference is that if you're going to positive infinity, then you're doing when x is greater than 0. In other words, you're changing x to the square root of x squared. Yeah, the square root of x squared. In other words, you're not going to get this negative sign here, right? So you're not going to have a negative sign. It's just going to be positive 3 over square root of 2, or if you rationalize the denominator, 3 square root of 2 over 2, right? So without having to do this whole horrible calculation all over again, that's the only difference here, is that because this is going to positive infinity, you don't get a negative sign right here, right? So that's the only difference. So if essentially we did two examples in one, right? This example, we're going to negative infinity, and in this example here, right, you're going to positive infinity. And the only difference is you lose the minus sign that we had from here. So I hope that helps. Again, if you have any questions, feel free to send me an email. But I think I'm going to leave it at this. This is probably the hardest example you're going to get. So I hope that does it for section 3.5.